Now we're going to talk about something called the limits of resolution and look at something that has been termed the Rayleigh's criterion. So when we look at two lights, you have a monochromatic light passing through a small aperture, and it shows this diffraction pattern. You can see the central median or central bright, and then the pattern that goes outside of that. So this is the light passing through a hole, and the diffraction that occurs. Now in B, you have two light sources. They're close to each other, and because they're close to each other, they produce overlapping diffraction. C moves these even closer together, and at some point you reach the experience that you cannot distinguish or resolve the two from each other, and this is called the limit of resolution. So if we look at this, this is passing through a single hole. So the graph of intensity of the diffraction pattern for a circular aperture is shown. Note that it's similar to a single slit. The central maximum is wider and brighter than those on the side. So what you have is with A is the circle as opposed to a slit. And instead of D being over lambda, it's going to be 1.22 times lambda over D sine theta. And this is because it's a circular slit as opposed to a circular hole as opposed to a slit. If you have two objects in a single slit, which is shown in B here, 2-point objects produce overlapping diffraction patterns as shown, and the Rayleigh's criteria is the minimum theta that can be distinguished. The central maximum of one pattern lies in the first minimum of the second one. You see the central maximum here looks at the first minimum, and so that is what determines Rayleigh's criteria. So a beam of light coming that produces this microwave transmission antenna will spread out at a minimum angle due to diffraction. It is impossible to produce a near parallel beam because the beam has a limited diameter. And you can see the diameter D, the angle is producing this. This is like from a circular aperture. You have theta, which is the angle that's produced for diffraction, and you're going to be back to that 1.22 times lambda over D. So if you're looking at something at a distance, you have 2 points that are separated by a distance x, and they are positioned a distance d away from an object. Then, in terms and symbols used to discuss the resolving power for the lens, the object is at point P. So you have here that the d represents the distance between the two objects of the diameter of the lens, and here's the resolving power of the lens. And so when you look at the geometric optics of this, the focus is at a point, but it's not physically possible to produce such a point because it implies an infinite intensity. And so it doesn't happen because intensity is not infinite. In wave optics, the focus is a region as opposed to a point because of the limited intensity. So let's take a look at how we would resolve problems related to this phenomenon. A 300-meter diameter radio telescope, and there's a picture in your book if you want to look at it, it detects radio waves with a 4-centimeter average wavelength. What is the angle between the two just resolvable point sources for this? All right, let's take a look at how we would do this problem. First of all, from the book and from my previous discussion, the key formula here is theta is equal to 1.22 lambda divided by d. Now, this theta is going to come out in radians, and I forgot to mention that when we were talking about it before. So we have to keep in mind that this is going to come out in radians as opposed to degrees. This is not the sine of theta. So we go 1.22 times, and the average wavelength is 4 times 10 to the minus 2 meters divided by 3 times 10 to the 2 meters. And if we do the math here, we get 1.6 times 10 to the minus 4 radians. So that's the angle. Now this second one is a little bit more complicated. If you look in the book, and I didn't talk about this before we got to the problems, but if you look in the book, you remember that when we're talking about an angle, the distance between two things is called S, and the distance away is R, and here is theta in radians. Okay, so that means that S is going to equal R times theta when you're working in radians. And so the question here is, what is the minimum diameter of a mirror on a telescope that would allow you to see the details as small as 5 kilometers on the moon that's 384,000 kilometers away? Assume an average wavelength of 550 nanometers. So if we start with this formula right here, then S is going to equal R, and then theta is going to equal this. So 1.22 times lambda over D. Now we're trying to find D here, so we have to solve this equation for D. So you multiply both sides by D. You get R times 1.22 times lambda, and then D is going to equal R times 1.22 times lambda divided by S. When we put our numbers in here now, it's 1.22, and now R is this distance, which is 3.84. Now that's 10 to the minus 5 kilometers, 10 to the plus 5 kilometers, so it's 10 to the plus 8 meters. Lambda is 5.5 times 10 to the minus 7 meters. And the S is going to be the distance between, which is 5 kilometers or 5,000 meters. And if you do all this math here, you get 0.051 meters or 5.1 centimeters as a minimum diameter on a telescope. Let's look at another phenomenon that occurs, and that is something called thin film interference. And you've probably seen this. You see these soap bubbles. You see what's known as what's called the light here. So when light is exposed, it causes various wavelengths in color to appear. So let's take a look at what this represents. Light striking a thin film is partially reflected. This is shown with the ray 1, and at the top of the surface, then a refracted ray goes through the surface of the thin film, and then is reflected and refracted back out. So you end up with 2 rays of light. And these rays then can interfere in a way that depends on the thickness of the film and the indices of the refraction of the various media. So for example, if you have 2 slides that you put together, a rainbow sort of color appears, and this is caused by the thin film interference with the air in the 2 glass slides. And B shows this schematically, the path that these various rays take in the process. So you see that ray 1 passes into the glass, it's refracted, it goes to the second slide, it is then reflected, and it comes ray 1 is reflected on the opposite side of the glass. Ray 2 goes all the way to the second glass, is then reflected and then refracted by ray 1. And then the second one on the right is a different ray doing the same thing, and it's called 1' and 2'. So this produces something known as Newton's rings. Newton's rings, interference fringes, are produced when two plano-convex lenses are placed together. That's what these are in the picture here. And their plane surfaces are in contact. The rings are created by the interference between the light reflected off the two surfaces as a result of a slight gap between them, indicating that these surfaces are not precisely in plane but slightly convex. So let's take a look at how we would do problems related to this. To do this problem, I'm going to refer you to the example 27.6 on page 975. I'm not going to go through all the justification that's given in this example for the sake of time, but the formula that's needed is 2t, where t is the thickness, is equal to the lambda in the second medium, in this case oil, divided by 2. In order to get destructive interference, you have to be out of phase, so you divide that by 2. And it's also true that lambda n2, that is the wavelength in the second medium, is equal to lambda in the first medium divided by the refractive index of the second medium, and then in this case is this. Now, that means that lambda in the second median times n2 is going to equal lambda. And the reason I say that is because it says it appears this way. And so we have to substitute 2t is equal to lambda n2, which is what we see, times n2 to find the actual to show what the actual, this is what is given as the blue wavelength. This is what it appears, okay? And then you put 2 in there. So t is going to equal to lambda m2 times n2 over 4. And so this is 4.7 times 10 to the minus 7 times 1.4 divided by 4. And the answer here is 1.65 times 10 to the minus 7, or 165 nanometers. So the thickness here the minimum thickness has to be 165 nanometers. Now if we look at the second problem here, the soap bubble is 100 nanometers thick, is illuminated white. What is the wavelength and color visible light is most constructively reflected, assuming that this refraction of index is the same as water. Now the refraction of index of water is 1.33. Now we have 2t is equal to lambda n2 over 2. Now we use this formula because now it's not what appears, but we want to know the actual lambda. So we substitute that in here. We get 2t is equal to lambda over n2 divided by 2. And now we have 4t is equal to lambda over n2, and lambda is going to be 4t times n2, or 4 times 1 times 10 to the minus 7 times 1.33, and this is equal to 5.32 times 10 to the minus 7, or 532 nanometers. Now 532 nanometers is right dead, it's above the blue range. It's getting into the green-yellow range, and you can look up the actual on a table in the book. The last topic we're going to talk about here is polarization. Here is what we're talking about when we're talking about polarization. What ends up happening is that light rays travel differently depending on which light ray it is, and you can see that some light rays have a oscillation in the x-axis, some light rays have an oscillation in the y-axis, and then obviously there are various other oscillations that can occur. So the transverse oscillations can pass through a slit if it is oriented in the same direction as if the slit is oriented the same as the oscillations. However, if the slit is oriented perpendicular to those oscillations, it will block all the rays from going through, or in this case, the rope from going through. So whenever you have a light ray, it essentially has random oscillations. A light ray can have oscillations in any particular axis. The bold arrows represent the direction of polarization for individual waves composing the ray. And as you can see that they disperse throughout. This light is not polarized, so there are various other, so you have all various types of oscillations. Now, if you have a polarizing filter, what you end up doing is you pass this light that has all this different polarization through a polarizing filter which has slits only in one direction. And you end up with light that has one polarized direction. And this is called polarized light. If you have two filters, you can rotate these filters in such a way that it has different effects on the light. And you can see in A, if all the polarized light passes through by the second polarizing filter, its axis is parallel to the first. It passes right through and you have polarized light in one direction. However, if, as in B, you begin to rotate the second filter, you begin to decrease the intensity, and it begins, only part of the light can pass through. And then once they're perpendicular, then no light can pass through and it shuts off. And this is what's shown in the various situations in part D. You have various levels of polarization, and where it is black is where it's actually perpendicular. One filter is perpendicular to the other. A polarizing filter transmits only the component of the white light parallel to its axis. So E cosine theta, and reducing the intensity of any light that's not polarized or parallel to the axis. And so you see that when cosine theta, when it's parallel, it produces a full intensity. Cosine theta or cosine is 0 when it's parallel. And any angle other than 0 will reduce the intensity by a cosine theta. So let me state that again. If the light has various intensities, and you can see that, or various axes, you can see that when it strikes the filter, if the axis of the filter is 0, that is it's parallel to the up and down, then cosine theta is 1, and so the intensity is full. And any deviation from that causes the cosine to be some number other than 1 and decreases the intensity. And if it's at 90 degrees, the cosine of theta is 0, and so no intensity goes through. If unpolarized light reaches a surface, when it's reflected in such a way as it becomes polarized, and it becomes polarized perpendicular to the plane. So it's partially polarized. If it passes into the surface, it is partially absorbed, and then what's left is also partially polarized. And Brewster's law states that the tangent of theta b is equal to n1 over n2. That is the tangent of the angle which will produce this fully polarized light is equal to the two refractive indexes, one over the other. So what is Brewster's angle for a light traveling in water that is reflected from crown? Now, just as a reminder, and I might not have been clear about this a few minutes ago, Brewster's angle is the angle in which, when reflected, the light is completely polarized. And so when we're calculating Brewster's angle, what we're calculating is the angle at which we would get completely polarized light. So on this first problem, these problems are actually pretty straightforward. The tangent of Brewster's angle is equal to the second median divided by the first. In this case, the first medium is water, the second medium is crown glass. So if you look those up in the table, you get 1.53 divided by 1.33. And if you take that division and the arc tangent of that, you get 48.8 degrees. The second question here, it says light reflected at an angle of 62.5 degrees on a gemstone and a ring is completely polarized. So it's telling you that Brewster's angle is 62.5. Is this a diamond? Okay, so if you take solve this equation for n2 is going to equal n1 times the tangent of the Brewster's angle. In this case, it goes from air to the gem, and so air is 1 times the tangent of 62.5. And if you do the math here, you get 1.92. Now, if you look that up in the table, diamond is actually 2.419. So this is way off from diamond. So the answer to the question is no. If you take this same gem and put it in water, then what would be the Brewster's angle to completely polarize the light? And then you use this equation again, tangent b, theta b, is equal to 1.92, which is what you just found, and 1.33 for water. And if you do the math here, theta b is equal to 55.3 degrees.